So, good evening, everyone. Now we are starting the second lecture for the chemical engineering principle. Today we will study or continue the mass balance or equations, um, mass balance problems. In this mass balance problems, we assume that it is a steady state process, no accumulation occurring in this process, and we also assume there is no chemical reaction. So at the end, we can use mass in equal mass out without any accumulation. We will use the degree of freedom as a way to develop our solution in the easiest way possible and the shortest route. In this example, we have two-stage separator where the feed stream F1 containing three components, benzene, toluene, and xylene. It enters the first separator. Through the first separator, mainly benzene was separated, 0.99 or 99% of the benzene was separated in the top stream. The bottom stream enters a second separator where the toluene was merely separated. It is 95% of the toluene was separated in the top, and small percent of benzene that was remaining separated from the top. From the bottom stream, it's mainly xylene, 90% xylene, and a smaller composition of toluene is 10%. What we want here is the mass flow rate of F2, the internal stream between separator 1 and separator 2. And we want the composition of this stream. So we want the mass flow rate of this stream and the composition of F2 stream. So first, let's see what is the degree of freedom and how to calculate it and use it to solve our problem. So for the first separator, we draw a system boundary across separator 1, where F1 is entering top product stream P1 and bottom product stream F2. First, we want to know the number of components that we have for this for process 1. So we have here three streams, benzene, toluene, and xylene, and two streams here, two components here, benzene, toluene, and other three components here, benzene, toluene, xylene. So we can say that we have a total of 1, 2, 3, 4, 5, 6, 7, 8 components. A number of additional relations, there is no additional relation given here, so it is 0. Number of balance equation, we can use, we have only 3 components, so we can say that we can do 3 material balance equation, benzene, material balance equation, toluene, and xylene. So it is a total of 3 material balance equations that we can do for this process. Number of given variables, we have here the mass flow rate of the inlet stream, and only 2 of the composition of the inlet stream can be considered, so it's 1, 2, 3. For this top stream, we can use only benzene, so it is a 4. Here we have no defined stream or no given variables here for the composition or the mass flow rate of F2 stream. So we can say that we have 4 given variables. Degree of freedom is 8 minus 0 minus 3 minus 4, so it will be 1. This means that we need 1 more defined variable or given variables in order to solve this process stream. What we mean by solve is to get the value of B1, F2, or 2, or to know all the unknowns. For process number 2, we do a stream boundary, system boundary around process 2. We have a feed stream F2, we have a top product stream P2D, and a bottom product stream P2B. Number of component here is 3, benzene, toluene, xylene, and for the top product benzene and toluene, for the bottom toluene and xylene. So we have 1, 2, 3, 4, 5, 6, 7. So we have total of 7 number of components. I have to point out here that sometimes the components are not written on the stream. So just it's giving F2 and with no component written, no benzene, no toluene, or no xylene, it's not written. And you have to know this component through the product. So you have benzene, toluene, toluene, xylene, so you know that the inlet stream should contain benzene, toluene, and xylene. Okay, so it is not a must that you will be given the inlet, the composition of the inlet stream, or the content of the inlet stream, because you can know it easily from the product, from the content of the. For the degree of freedom here, so it is 7 minus 0 minus 3 minus 2, so it will be a total of 2 degree of freedom. This means that we need 2 unknown. So in this case will be P2B and P2D to be known in order for us to solve this problem, to know or to get the value of the inlet stream. Okay, so this is what is meant by degree of freedom. For the process, this is a new thing. I want you to understand how to calculate the process. At the end, you have in your process the degree of freedom 1, and in the for the process number 2, it is 2. So sometimes you get a doubt that the process will be solvable. So how to know that the process will be solvable or not? So the steps is as following. So number of components, now we are considering the whole process. Every stream, even internal streams in this process are being considered. So the number of a number of components here for the process, we have 3 components here, 2 components here, and 3 components here. So it is a total of 8. So and 2 components here, so 9, 10, and 2 components in the top is 12. So we have 12 number of components for the process. Number of additional relation here is 0. It's not always 0. In the recycle, we will find that we, or in the splitting point, we will find that we will use sometimes the additional relation. We'll consider it as 1. This will be in example 5, I think, for this lecture. And so it depends if it is given any information else than the drawing is given, like a relation between the benzene output and the inlet one. So this will be considered an additional relation. Any relation away from other than the mass balance equations. Number of balance equation for this, it will be considered 3 plus 3. So it is a total of 6 process. So in this case, just note, because it is a different here in when you are calculating the degree of freedom for the process, it is 3 plus 3. Okay, so it will be total of 6. Number of given variables here, we will do it for every stream in the process. So it is 1, 2, 3, 4, no here, no given here, 5 and 6. So it is a total of 6. So the degree of freedom 12 minus 2 minus 6 minus 6, and it is a total of 0. So this means that the process, our process, is solvable. We can go on and do the overall system boundary. We will draw a system boundary around the whole process. The stream that we will consider only the stream that is crossing the system boundary. This stream will not be considered because it is an internal stream. It's not crossing the system boundary. So for F1, it's crossing the system boundary. For P1, it's crossing the system boundary. P2D is crossing the system boundary, and P2D to B is crossing. So these 4 streams only will be considered. This stream, inlet stream, will not be considered because it is not crossing the system boundary. For the number of components for the overall, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is a total of 9 number of compounds. Number of additional relations is 0. Number of balance equation, how many material balance equation can we do for this overall process? It is a total of 3. We can do 3 individual material balance equation or mass balance equation, or we can do 1 overall material balance equation and 2 individual material balance equation. So at the end, you have all 3 components. It is the same as the number of balance equation, it's 3. Number of given variables here is 9 minus 0 minus, number of given variables here is for the stream 1 is 1. The mass flow rate is given. Only 2 of the components will be considered because the third is directly known. It is known. So for this mass flow rate will be considered. 2 of the composition will be considered. So 1, 2, 3, 4, 5, 6. Okay. So the overall degree of freedom here is 9 minus 0 minus 3 minus 6, so it is a total of 0. So the degree of freedom, our key here is the overall process. So what we are going to do here, so we know from the degree of freedom that we should start with an overall, to do overall material balance and use the overall material balance equation. So the system boundary should be drawn around the overall. This will be, this will yet let you know the values of B1, P2B, and P2B. If you know these values, you can easily know the value of F2. So let us think about how to know F2. So which process can we use? Which system boundary can we use? We cannot do the overall. So overall will not give us anything about F2. Okay. Still, we need to conduct to do a material balance.
Doctor, we are not getting you.
I'm sorry. But for this process, if we either want to draw a system boundary around F1 or system boundary around F2, what does the degree of freedom tell us? For the system boundary, if you draw a system boundary around process 1, the degree of freedom is 1. This means that one of the unknown should be known. In order to, the number of variable here, instead of 4, should be 5. So the degree of freedom will be 0. So which of the unknown here? So we want to know B1. Okay. So if you are using the degree, the overall, you can get the value of B1. Or if you want to use the process 2, you want to know two unknown. So two unknown should be known or given from the overall. So in this case, for the overall, you should know B2B or B2D. Okay. So let's start here. Okay, there is a question here. I'm sorry. Okay. So for this so for the overall, we will start according to here is overall. Okay, so we'll start with the overall according to the degree of freedom. Degree of freedom is 0. So overall, what will the overall give us? Or which way should we start with the overall process? Shall we start with the total mass balance, or we start with component mass balance? Which component, benzene or toluene or xylene? A closer look, you can see that the xylene is produced here. Xylene is not produced here. Xylene is not produced here, but xylene is coming out from this stream. It's not a component, it's just a component of this stream and this stream. So it can be considered as a key component. So xylene is a key component, and it will be easy to start with xylene. So let's see this. So this is xylene mass balance. We will conduct a xylene mass balance where the mass fraction of xylene is 0.2 times the mass flow rate of the stream F1. This will give us the total mass of xylene in, and it is equal to the total mass of xylene out. Okay, total mass of xylene out is 0.2 times P2B. So for this, it is written here in the mass balance here. So we can easily calculate the P2B mass flow rate. Okay, the other thing here, what we can consider is, okay, benzene. We can do benzene mass balance. Why benzene? Because benzene is only written here, produced, or one of the component of P1 stream and one of the component of P2D stream. It's not in P2B stream, so we will, here will reduce the number of steps that you are using. So doing a benzene mass balance, the total amount of benzene in equals the total.
Doctor, no voice, no voice. We're not getting you.
I'm sorry. I'm sorry. Okay. So the total number of benzene in equals the total number of benzene out. So the mass fraction of benzene times the mass flow rate, total mass flow rate of component F1, of stream F1, this here, equals the total mass of benzene out with the mass fraction of B1, mass fraction of benzene times B1, plus mass fraction of benzene times B2D. Here you will do a relation of B1 between B1 and B2D. Now we can do a total mass balance. You remember we can do 3 mass balance equation: xylene, benzene, toluene, or total material balance equation. So we can do total mass balance equation F1 equal B1 plus B2D plus B2B. Okay. For the WF and A, it is written. It was a mistake. It's not correct. It's not written here. I forget to omit it. So we substitute with the value of F1 for B1. We will use this relation, okay, here, and B2D is not given for the W for the B2B. It is already known here from this equation. We get the B2D. Now, what we know here this value, the mass flow rate of B2D, the mass flow rate of B2B. So this will give us 2 variables. Will be, instead of unknown, it will be known. So this makes us we can use now the process 2. Okay, we can do a system boundary around process 2, and the process will be solvable. Okay. So now we can do for process 2, we can do a total mass balance F2 equal P2D plus P2B. Now we can get F2. Okay. And then we can do benzene or toluene, either xylene or I'm sorry, xylene is better. Xylene, it is not a product here, so it will be only a product here. So the inlet xylene equals the outlet xylene. So mass fraction of xylene times F2 equal mass fraction of xylene 0.9 times P2B. We can now calculate the mass fraction of xylene. The same can be done for benzene, because benzene is not a product from here, it is only a product here. So it will be a shorter step. If you use the mass balance on toluene, using toluene is fine. It will be calculated. It's fine. But the problem is that the steps will be slightly more. So for the benzene, the total amount of benzene in equals the total amount of benzene out, and you can calculate it and get the mass fraction of benzene. And also for the toluene is 1 minus mass fraction of xylene minus mass fraction of benzene, and you get the mass fraction of toluene. Still, you are not getting my voice? Okay. So as you can see, this is how we can use the degree of freedom to do our step, to develop our steps for solving the problem. Okay. One of the other important thing for chemical engineering, or you will be in any process or any plant or industry, refinery industry, you will find recycle. So why recycle? But we know without chemical reaction. So in general, you get your feed in to the process, either reaction, and then the product out. For the recycle, you get some of the product separate of some of the product or unreacted reactant, recycle it back with the feed. So this is why recycle is used. In most cases, recycle is used to recycle the unreacted reactant. For example, for the industry of ammonia, production of ammonia, we have nitrogen reacted with hydrogen, and the output will be, or the product will be ammonia. With the ammonia, the conversion is 22 to 25%. So what is the risk? So this means that we have 75% of the feed unreacted. We cannot use this as a product, so they will enter separator. So the gases will enter separator, separate the nitrogen and hydrogen from the ammonia, and recycle it back with the feed to enter to the reactor again and have another cycle of reaction. This is one of the important things for recycle. Recycle is so it is to recycle unreacted products, unreacted reactants. One of the uses of recycle is the catalyst. So some of the reaction have like the fluidized bed reactor. Some of the catalysts go with the product, and you have to use a cyclone and recycle the catalyst back to the fluidized bed reactor. Other thing is the fractionation column. If you're on the distillation column, the top gas, you will enter. So the top gas enter a condenser, and the condenser, the vapor converted to liquid, and you use some of these products. Some are used as a product, and some are recycled back to the column or distillation column. So okay, if you know that recycle are used to control the temperature. So this was the main. It's not unreacted in the case of distillation, but it has a function. The function is to cool down or to adjust the temperature of the distillation column. So recycle is important in the chemical engineering or petroleum refinery or petrochemical. So it is in general it is important, and it will gain money when using recycle. This is one of the example of recycle. So this is converting naphthalene to phthalic anhydrates. So for the reactor, the products are produced, but there is unreacted reactant. So sometimes you install a separator and use the unreacted reactant injected with the feed, and we enter together the reactor and do another cycle and cycle and cycle, and so still you can get unreacted reactant with the product, but it is with a smaller concentration. Instead, for example, to getting, for example, like 40% of unreacted reactant with the product, you will get it like 10%. So you are reducing the amount of unreacted reactant coming out of the product. Also, one of the important points is the mixing point and splitting point. For the and we will see it how it is applied in the recycle. But the mixing point, where you have two streams combining together, this combine and getting one product stream. They can enter, or we can represent a mixing point as a rectangle or square, or you can represent it as a point. So it is two feed stream coming out as one product, combining as one feed stream. As a reverse is the splitting point. So the splitting point is one feed stream, then separated to two streams, whatever. This separation can be represented with a rectangle or square, or can be represented with a point. So one inlet stream, two exit stream. For the splitting point, the composition of the inlet is the same as the composition of the exit one. Okay, splitting point, the same composition here, the same composition here, and the same composition here. For the mixing point, it is different. It can be a different composition, and different composition. We'll see it now. As example of this, so we have a raw milk, okay, containing 3.8% fat. It entered to a centrifugal and separated. So the cream are separated from the rest of the milk. So you have a stream, top stream as a cream containing 30% fat, and bottom product is skinny milk containing 0.01% fat. So the cream are produced from the top, and then you get through a splitting point. There is a splitting point here. Some of the cream are used as a product, and some are used here as a mixer. It's mixed with the skinny milk. You can see here the composition of the inlet, 30% fat, the composition of the product, 30% fat, and the composition of the other stream, stream number 5 is 30% fat. So for the splitting point, it is all the same composition, okay? For the mixing, it is different. So for this, he used a cream, 30% cream, to adjust the fat percent of the milk. So it is 0.01 fat entering, combined with milk of 30% fat, they end up light milk. So you can adjust the fat percent of the milk using the mixing point. Okay, so it is skinny milk, it's 0.01 fat, different compositions than the other inlet stream, which is 30% fat cream, and the outlet is light percent milk, 20% fat. Okay, so for the splitting point, all are the same composition in all the cases. For the mixing point, it is a different composition. Okay, so for the recycle, we now understand the recycle. But how to conduct a material balance? It is the same case. You do a material balance around the mixing, a stream boundary around the mixing point, stream boundary around the process, stream boundary around the separation, and overall system boundary. Okay, so it is a system boundary around the mixer, system boundary around the process, system boundary around the separator, and overall system boundary. It is the same. Consider it as any normal material balance equation. Other important definition is the bypass. Bypass, we have a feed entering a process, either reactor, whatever, and exiting as a product. What's meant by bypass is you have a splitting here, so its feed are split in two streams. The other stream is combined with the product. For example, to adjust the specification of the product. Okay, so you want to the amount of, for example, the amount of fat of the milk that we just give an example about. So this is one of the definition in feed are splitted and are combined to two streams. One is stream enter to the process, the other stream are combined with the product. One of the other definition is a purge. For the purge, the feed enter the process or reactor and we get a product. Sometimes you install a separator and you recycle the unreacted component with the feed, and we enter the process again. Because you, in most cases, you have inert gases like the argon. There will be accumulation of the argon inside the system, inside your system. It will not be reacted. It will not react. Oh, I'm sorry. So it will be accumulating, increasing the percent, and with this will affect your reaction. So you do purge. So for the separator, after the unreacted gas are separated, some enters as a recycle and the other is purged. You will find this in the industry of ammonia also, and you can also find the purge in when you are closing your process. You have to use nitrogen or steam or air, and sometimes water as a purge. You want to get rid of the amount of hydrocarbon inside your pipeline. So you use a purge concept. Okay. Okay, so one of the questions that I think it's a previous slide, some is asking that we have carbon dioxide. Yes, okay. This will come from a reaction. The reaction. Oh, okay. Carbon dioxide, there is no carbon. Yeah. Okay. Maybe there is a C and there is a mistake, but you are right. C should be entering, CO2 should be entering. We cannot get C. You are right. Thanks. Thanks, Emmanuel. Thanks. Okay. For this, we want to introduce the concept of bypass, purge, recycle, mixing, and splitting. So let's see here. We have a feed here, fresh feed. We get some of the fresh feed to combine it with the product. So this is the reactor, and this is the product from the reactor. The fresh feed are combined with the product through a splitting point. So stream number 1 is splitted to stream number 2 and stream number 3. The composition of 1, 2, 3 are the same. Okay, and then they are entered to the reactor. Some of the product are separated. So it is entering in the, with the product through a mixing point. So it is stream 2 are mixed with stream 5, and we get stream 6. They have to be different composition. This composition is different than this, is different than this. So this is the mixing point. They enter to a separator. Unreacted gases are recycled back here through a mixing point. So inlet stream 3 with stream 9 combined to enter the reactor with a stream 4. So this case is a recycle. So unreacted gases are recycled back. Some of the recycle, because they contain inert, are separated through a splitting point. Okay, so it is a splitting point here, combined together here, as a purge stream. Okay, so this is one of a diagram combining all of the concepts, the bypass and purge, recycle, mixing, and splitting. For this problem, we have a distillation column. So this is example number 4. We have a distillation column. We have, as a feed, is 10,000 kilogram per hour. We have the composition of the feed benzene and toluene. Okay, this is written here. It's written here. Through the distillation column, we have a top product as a vapor. Of course, the benzene will be the top, the main component in the top, 95% benzene and 5% toluene, with a mass flow rate of 8,000. And we have a bottom product of benzene and toluene, mainly toluene in the bottom, with a mass flow rate is unknown. The top product enter a condenser where a complete condensation occurs. What mean by complete condensation? That all the vapor are converted to liquid, okay? But will be the same composition. So the benzene, 95% benzene will be here 95% benzene will be here 95% benzene. So all the vapor are condensed with the same composition. Then we get a splitting point here where some of the condensed liquid, okay, after condensation, get it as a product D, and some are recycled back to the distillation column. It is written here, assume that this composition of the streams at the top of the column V, the product withdrawal D and the reflux are identical because the V stream is condensed completely, considered as splitting point. So they are identical, they have the same composition, okay? And this will be considered as an additional relation. So this is additional relation for the splitting point, for this splitting point, okay? What we want here is to find the ratio between the recycle and the withdrawal product D. So for this problem, we want to find R over D. For this point, we will do the degree of freedom first. For this problem, we want to find the amount of reflux as a ratio with the withdrawal product. So R over D. We will do the degree of freedom. We have the splitting point here. We have the distillation column here, and we have overall. Okay. If you have any question, I will take the question. Just this is the end of the last exam, and I will take all your question and inquiries at the end. Okay. So for this splitting point, or the degree of freedom that we can do, the number of components here is for the inlet is 2 components, benzene and toluene. For the exit stream, D, benzene and toluene, and for the reflux is benzene and toluene. So it's a total of 6 components. Number of additional relation, here is the point for the recycle, or for the splitting point, we will take 1 additional relation here. This additional relation is taking because he is giving us that all for the splitting point, all the composition of the streams are identical, are the same. Benzene toluene, this is 0.95 benzene, 0.05 toluene. For here it is 0.0595 benzene, 0.05 toluene, and for the reflux it is 0.95 benzene and 0.05 toluene. Okay, so this is considered as an additional relation. So for this, for the splitting point, we will take 1 additional relation, but we will now
Sorry, doctor.
we will not get this as a will not add this in the given variable. We will see. For the number of balance equation, we have 2 components, benzene and toluene. So for this we can do 2 material balance equation. And for the given variable, we have here the mass flow rate of the inlet vapor. We have the the liquid. We have the composition of benzene and toluene is taken as 1. So we have the mass flow rate of vapor and 1 of the composition of benzene. We know that it is here 0.95 and it is here 0.95, but we will not take this as a given. We already consider this in the additional relation. So for the given variable, it is 1, 2.
Doctor,
Yes.
I can't understand this table.
Okay, for this rule, it is for the splitting point. It is only applicable for the splitting point. Okay. For the splitting point, we have a rule saying that the composition of the inlet stream is the same of the composition of the 2 exit stream. Okay. So the composition of benzene and toluene here in the inlet is the same as the composition of the benzene and toluene in the reflux and the benzene and toluene in the withdrawal product. Okay. Now we consider it as 1 additional relation. This is one information, one piece of information that all the streams are identical. Okay, for the V, for the R, and for the D, all are the same composition. So this is considered as 1 additional relation. Okay, type. When you go to calculate the number of given variables, how many of the variables are given? You are given here the mass flow rate. You are given here the composition of the inlet stream for the mixing point. This will be considered as a given, but for the D and the R, we will not consider this. We will not take this because we already used it in the additional relation. Okay. Okay. So so the number of given here is the vapor, 8, and the benzene. For the toluene, it will not be taken. It doesn't give any. It's not given. Okay, it's not effective. So 1 and 2. So it is 2. No here, no given here, and no given here. So the degree of freedom here is 6 minus 1 minus 2 minus 2. It will be 1. The degree of freedom will be 1. Try and solve it, and we will not be able to solve it. For the recycle stream, or for the splitting point, you can do only one material balance equation is effective. How? Because all are the same composition. Try for the total mass balance. You have 8,000 kilogram per hour vapor inlet. You don't have equal D plus R. V equal D plus R. Okay. Let's do individual mass balance equation. Individual will tell us 0.95 times 8,000 equal 0.95 times D plus 0.95 times R. It is the same as the total material balance equation. It's not effective. Okay. Okay. So if you want to another way to do it, if you want number of balance equation, you can reduce it to 1, and the number of given variable you increase it to 3. But it is not. If it tries just to stuck to what I'm telling here. Okay. For things not to get, it will be more complicated. So just stuck what I'm telling you. This is the easiest way to think about. So for the splitting point, you will take one additional relation, and you will only consider one of the composition of for one stream only. The other two stream you will not. You will put your hands on them. You will not consider them. You will not see them. Okay. Okay, for process number 2, we will draw a system boundary around the distillation column. We will consider only for the streams that cross this boundary, F and V, R and W. Again, for the splitting point, the additional relation works only for the splitting point. As here, for this system boundary, the splitting point is not inside, it's not considered. Okay, so we will take this composition as given. It's not one of the splitting point. Okay, we will deal with just a stream R crossing the boundary, stream V crossing the boundary. You will put your hand on the splitting point. You will not see the splitting point. For the number of given variables here, number of component 1, 2, 3, 4, 5, 6, and 7, 8. So it is 8 component. Number of additional relations, there is no additional relation because the additional relation was only for the splitting point. Number of balance equation, we have 2 components. We can do 2 balance equation. Number of given variables, we have 1, 2, 3, 4, 5, and 6. This will be given because it is 0.95. It's identical. So the degree of freedom here is 0. This means that we can solve for any unknown here. Any unknown here for the R, I can know it. For the W, I can solve and know it. Okay. Again, just for revision, the process is solvable. So number of variables, or number of components for the process, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number of additional relation, we have 1 additional relation for the process. It is here. Number of balance equation, it is 2 plus 2, so it is a 4. Number of given variables, it is 1, 2, 3, 4, 5. Okay, but you have the splitting point in the process, so it is just only 5. 10 minus 1 minus 4 minus 5, it will be 0, the degree of freedom 0. This means that the process is solvable. You can solve the process. You can know any unknown in the process can be known. The last system boundary will be the overall system boundary. We have only the feed here, the D and the W. These are the streams that crossing the boundary, system boundary. The V and the R are internal. It will not be considered. Internal, it will not be considered. We just only consider the streams that are crossing the boundary. For the overall number of components, 1, 2, 3, 4, 5, 6. So the number of component is 6. Number of additional relation is a splitting point will not be considered here. It's just we are considering only the system, the streams that are crossing the system boundary. So it is 0 additional relations. Number of balance equation, we have 2 component benzene and toluene, so we can do 2 balance equation. Number of given variables, we have here the mass flow rate of the feed. One of the composition only will be considered, so it is 2. One of the composition here, 3, and one of the composition here, we know the benzene is 0.95, so it is 4. This means that the overall process can be solvable. It is 0, so we can use the overall process to get the value of D, and then we use the splitting point to get the value of R. Okay. And if you under sort of So for this, we will do overall process. We will get D. Okay. So the D will make the process here, the splitting point here, instead of the given variable, because D was unknown. So D will be now known if you solve it through overall. And the number of given value instead of 2 will be 3. And of course, the degree of freedom now will be reduced to 0. If you know one of the given here, on the splitting point, the degree of freedom will be 0. Let's see. So we'll start with the overall process. We will do overall material balance. So if F equal D plus W, we know the F. We can make equation between W and D. Benzene material balance or toluene material balance, both can work. The number of benzene in equals the total amount of benzene out. The amount of benzene in equal total amount of benzene out. So now the amount of benzene in the mass fraction of benzene times the mass flow rate of the stream, 0.05 times 10,000, equals the amount of benzene on the top products and the amount of benzene in the bottom product. At the end, you can know the value of D. Okay. As we know D, we can now use or do a material balance around the splitting point. For the splitting point, the only material balance equation that we can use is V equal D plus R. This is the only material balance equation that we can use. We cannot use component material balance. So V equals D plus R. We know now the value of D, and the value of V is given, so we can use them to get the value of R. Now R over D, we get what we want. So one of the requirement for this is to for this problem is to get R over D. So it's 0.58. Now you solve it the problem.